Section 39, volumes with the disk and washer method. So first of all, I put a lot of stuff on here well, the pictures here are related to washers. That's when we have a hole in our picture. So, for example, like a soccer cone has a big hole in it, and so this would use this method. A bowl has rotational symmetry, and it has a hollow inside. A water glass has a hollow inside, and that's stuff we use the washer method for. Things that are solid, we do not use the washer method for. So like the bumps on the road, the round ones that often go between lanes and stuff, those bumps have rotational symmetry and they're solid. So those would be an example of something we'd use the disk method on. The disk method is just integrate pi r squared. And the washer method is find the analysis, which is the difference between the two curves, or just do pi big R squared minus pi little r squared. If you remember from geometry, that was the way we found the area of this donut type shape. And the way we're applying this to now calculus is we're finding the 3D, because donuts are 3D, they're not 2D. Version of this. So you're just using the same equation. You're integrating pi big R squared minus pi little r squared for the part you're subtracting out of the middle. So let's do an example problem. So the graph below, which doesn't exist yet, is square root of x, which looks like so, between 0 and 1. Between x equals 0 and x equals 1, yeah. Use the disk and washer method. Cool. So we're going to rotate this over a whole bunch of things. We're going to do more than just the problem there. We're going to do x-axis. We're going to do y-axis. We're going to do x is equal to -3. And we're going to do y is equal to 10. We're going to do 4 different integral problems here. We're starting off with the easiest one, because x-axis, if I rotate this around, is actually a disks problem. We don't have a hole in this shape. So for the x-axis one, I'm going to be integrating from 0 to 1 of pi r squared, where r is just the height, which is root x. So really easy integral. This is the integral of x dx, because the square root of x squared is x. And so we get x squared over 2. We're plugging in 0 and 1 and multiplying by pi, so it's pi over 2. Alright, the easy one is down. Sorry, went off the page there a little bit. Pi over 2 is our final answer. Y-axis starts getting a little more interesting. The way it gets interesting is by rotating this shape across this axis. We're going to end up looking like this. That's my rotate. So it's going to go across like so. And we're going to have a hole here. This is like a gap that we have going on here. And so we need to subtract that part out. So that's going to be our pi little r squared, is whatever this radius is that gets us out to this edge. Whereas our pi big R squared is just going to be 1, like a cylinder with radius 1. So it's going to be the integral of pi big R squared, which was 1 dy, because we are in the y direction. And we're integrating from 0 to 1 in the y direction because we also go up 1 in this shape. It turns out the square root of 1 is 1, so nicely we are what we're integrating from and to doesn't change. So that's pi big R squared. Now we're subtracting pi little r squared, which is from 0 to 1 of the inside radius. The inside radius here is my graph, my picture, my curve. So that's going to be x is equal to y squared, because we're solving for its x value, because now we're in the y direction that we're flipping. And so we actually get y squared squared dy. One note, this was 1 squared dy. I just didn't write the 1 squared because it's 1. But yeah, it is 1 squared. So it's still pi big R squared minus pi little r squared. And remember, this is smaller from 0 to 1. Now I just solved these two integrals. So this is, whoops, I'm ready to integrate both of these. This is from 0 to 1 of y, cool, minus pi from 0 to 1. This is y to the 4th, so I just get y to the 5th over 5. Now I just plug in my bounds, and I get pi, because I just plug in 1, minus, I get 1/5 pi. And so really, I get 4/5 pi here. So we actually get more volume rotating this guy over here than we did rotating this around here. And the reason we do is way more obvious if you spin into 3D. Here, our smallest part is what we're actually rotating around the edge the most. And the stuff around the edge, because the circumference is much smaller or much larger as you get to the outside here, multiplying that by a bigger number like we do when the bigger edge is now what we're rotating all the way around will actually make a bigger shape. So this thing is quite a bit bigger. It's almost double our x-axis way. And it makes sense from the picture if you can visualize what these things look like when spun into 3D. It's quite obvious that this guy, because it's taller near its edge, it's flipping the longest way around, it's going to be a bigger volume because it's spreading that out more. All right, now we're going to flip across more lines. We're going to flip across x equals -3 and y equals 10. So starting with x equals -3. X equals -3 is over here, like way over here in my picture. X equals -3 is actually a y-type problem because x equals -3 is parallel to the y-axis. So we're actually going to keep things in y's. And now our radius from -3 all the way over to 1 is actually 4 long. It's a 4 long radius. And our radius to the short side, I should redraw this for clarity's sake so we can actually see our picture. So here's y equals -3 over here. And our long radius is 4. And our short radius is, well, this distance is 3. And this distance is y squared. Just like in this problem, our previous problem. So when we do this, pi big R squared is going to be pi 4 squared. Because that's our big radius, is all the way out to that line, which is 4 away always, because it's flat. It's straight up and down, or parallel. Dy, and we're going to be subtracting pi times the integral from 0 to 1. Both of these are from 0 to 1. What we're integrating from and to doesn't change, because the height of the actual graph doesn't change. Minus 3 plus y squared. Squared. So that's our little radius squared, which was 3 plus y squared because this part was 3 and that part was y squared. All right, these aren't terrible integrals to solve. I got to expand this one first. But this one's just going to be 16y when I integrate it. And so this one's just going to be 16 pi. So that one's pretty easy. Now let's do our other integral. We'd subtract. We aren't ready to integrate yet. We got to square this. We get 9 plus 6y squared plus y to the 4th dy. And we integrate that, and we get from 0 to 1 of 9y minus 2y cubed plus y to the 5th over 5. Now we plug in our nice bounds of 1 and 0. 0 does nothing, but in this case. But 1 gives us 9 pi minus 2 pi and 1/5 pi. But all of this stuff is subtracted from 16 pi. let's actually figure out what this is. So inside the parentheses here, I get 7 pi plus a fifth pi. So this is 7 and a fifth pi, which is 7.2 pi. So this is 16 pi minus 7.2 pi. So this is actually 8.8 pi. So this one is significantly bigger than the previous one we did. When we flipped across just the y-axis, we only got 4/5 pi, which is 0.8 pi. Now we get 8.8 pi. That's quite a bit bigger, like significantly bigger. And it's because we're shifting across a farther line, so our radius of our donut is way bigger. So this would be a much bigger donut contraption thing here. All right, we have one last picture. We're rotating across y equals 10. I'm going to flip to the back side to do this. Y equals 10 is way up here, and I got to draw my graph nice and small down here. So this is my outside radius. It's just always 10 away, because from 10 down to 0, which is the bottom side of my little shape that I'm flipping around this. And my short radius is down to the graph, which was root x tall. But it's not root x tall. It's 10 tall minus the height of the graph, which is root x. So it's actually, my little radius is 10 minus root x. And so when I set up my integral now, it's going to be the integral from 0 to 1 and a pi. We're going to do pi big R squared. Big R was 10. And it's back to dx because it's like the x-axis. It's parallel to that. Plus pi from 0 to 1 of our little radius squared. Oh, I meant minus. Whoops. Pi big R squared minus pi little r squared. So we're going to subtract the little one. 10 minus root x squared dx. Now I'm going to solve this integral. 10 squared is 100, so this is 100x with 0 and 1 plugged in, pi, and we just get 100 pi. So that's our big radius. A quick side note, the big radius is easy to find when it's just a cylinder like this, when this side's parallel to the side you're flipping over. It's just pi times 10 squared for So it's a cylinder with radius 10, so you just go, okay, height 1, so it's pi r squared h, and that's 100 pi. And so we could also do it that way, but this is kind of proof the calculus works. Look at that, it works. Okay, very exciting. So yeah, pi r squared h for cylinders. It can save you some time if you want to use cylinders instead of actually doing the integration. But for the other part, we need to do the integration. And we also need to expand this out. So it's 100 minus 20 root x plus x dx. Was not a bad squaring to do there. Now I can integrate 0 to 1 pi, and we get 100x minus, okay, this is x to the 1/2, so I get 20x to the 3/2 divided by 3/2 and plus x squared over 2. And all this stuff is stuff we're subtracting. So I get 100 pi minus, if I plug in 1, I get 100 pi. Well, that part kills the other part. This term, I get, okay, 1 plugged in, I just get 20. And this is 20 times 2/3, so it's minus 40/3 pi. And if I plug in 1, I get 1/2, so it's plus pi over 2. And since these actually kill each other here, all we get is 40/3 pi minus pi over 2. If I want to like finagle this, I should get common denominators. 80 pi over 6 minus 3 pi over 6 equals 77 pi over 6, which is 12 and 5/6 pi, or 12.8333 pi. So this guy was actually our biggest of the bunch. If you remember back on this side, 8.8 pi. Yeah, that guy's smaller. And the reason is because we're rotating across a line that's farther and farther away. It makes the radius of our rotated donut thing bigger and bigger, and so it's going to have a bigger volume, even though this rotation was the way that originally made us have a smaller shape going across the x-axis line. And that's it for this video. This is how rotations work. Always think of things in terms of outside radius and inside radius, with the outside radius being the farthest point away, the line that represents the farthest point away, and the inside radius being the line that represents the closest points to the center, or the line of rotation. And that's how we always do our radiuses. That's it.